Hi, my name is Ben Christensen, and I'm going to show you how I created this vertex animation wall build using Houdini and Unreal. Inside Houdini, you can see that I've imported these glass wall meshes, and then I want to give a name attribute to each one of these. So there's 12 of these glass wall planes total, so that means 12 names. So I'm going to do that with an attribute wrangle for each one of the primitives. So if I go to the geometry spreadsheet, you can see that I have 11 names total from glass 0 to glass 11. And then what I need to do is I need to create constraints for these planes. So what I'm going to do is I'm just going to create a simple tube like this to go around. I'm going to set a mountain just to add a little bit of offset to this. And then I'm going to extract points. And I want to use points to create where I want the glass to have its fractures. But I don't want them to be super uniform like this. I want them to be random. So I put down a random selection, and it's just going to pick a whole bunch of these randomized points. And these points are going to be used to generate where the cracks in these glass walls are. And I put down an array for the minimum distance. And then I set up my glass fracture here, which is going to create all the fractures within these walls. So inside here, I just have radial crack of 3, minimum width of 1, and then I've turned off chipping because I don't want any really small points in this. And then I've added a little bit of detail for this. Next, I want to cache out the constraints and the geometry from this. So first things first, I just need the first frame because there's no animation yet. So I just have one frame of just this geometry with all the cracks in it. You can see it's coming out of this part of the glass fracture. And then the second cache that I'm going to make is for all of the constraints that I have set up within the glass. It looks just like this. And for the left side, for this fractured geometry, I want to add vertex color to the outside and inside of these pieces. That way I can get control over it within Unreal. So I'm just going to put down a color node first, and I'm going to say for all these inside pieces, remember this group inside is created by the glass fracture. And for all these inside pieces, I'm going to set it to vertex because I'm going to be using this vertex color, and I'm going to set it to blue. So we'll be using the blue channel for the vertex color once we bring this inside of Unreal. Then I'm going to set down another color, and I'm going to set the outside to be black. So the vertex color here is black and blue. And I'll be able to have more control over these colors within Unreal. And then I'm going to do an attribute promote. I'm going to promote the class primitive to vertex and delete the original. And then I'm going to set that to be, and then I'm going to set each plane for each class that we have here to be a different shade of red, and that's just how strong it is. So it's taking a value of 1 for red, and then dividing each class by what number it is inside our geometry spreadsheet. So each one of these has a different shade and strength of red from 0 to 1. And then we'll be able to use this later inside Unreal to control which one of these planes is activated at what time based on the strength of its red color value. So once that's done, just go to my attribute, and I'm taking the CD and I'm renaming it to CDV. And then with my glass constraints and this, I'm going to do an RBD configure to start setting up its destruction. And then I do RBD constraint properties. And I'm setting how stiff these pieces are and how strong the constraints are between them. And then I'm setting the V for the velocity, and I'm setting the W for the rotational velocity of each of these points here. Then I created a DOPNet, and inside the DOPNet, I'm bringing in this geometry, I'm setting up gravity, and I'm just running this as a simulation. So as you remember, we've set up velocity and rotational velocity. So all of these pieces, they're not falling straight down. They each have randomized velocity and rotational velocity. So they have a more interesting way of falling down to the ground. And I also set my gravity to 12 because I wanted them to fall a little bit faster. Next, I brought those here with the stop import, just these walls. And then with the attribute delete, I deleted all the attributes that I don't need, cached it out. Now let's create a time shift, and we're going to create a for each loop. And we're going to use this for each loop to generate a point attribute called radius. And then we're going to use that radius inside of blueprints to tell each piece when to start its vat animation. So you can see that I've created a point attribute called radius. And if I attach this sphere into the for each, you can see the radius of every single one of these points. So when our projectile hits or interrupts these point radiuses, that we'll be able to set it up so that the piece will begin its animation. I'm going to hook that back up. And then we're just going to copy this point attribute into our geometry. Just like that. And then we need to create a labs vertex animation textures node in the output. And here's my target texture width. And we're going to export this and include the geometry position and rotation. We're going to export this, and then we also need to export the first frame of this. So you can see that the second one, which is just going to be our first frame of this vat animation, we are including in the alpha that radius point attribute. Make sure that you have this decide individually. And in the advanced tab, you want to crop textures for first frame because we only need the first frame of these textures. Now let's bring this into the content folder of our Unreal project. Here in Unreal, you can see that I've imported my textures, and I'm just going to show you how I set up the master material first. So inside the master material, the first thing you'll see is that I have the vat rigid bodies node here, and I've plugged in the normals, the world offset position, and I have the UV1, 2, 3, 4 plugged in here. I've also turned off the tangent space normals. You can have this unplugged. Basically, you just want to make sure that the UV1 just doesn't have anything going into it. You can just put it in here for safety to make sure that you're not using it, but it's up to you whether you want to plug this in or not. I'm just going to leave this here. And as you can see, if you look at the simulation, the outside of this is white and the inside of this is blue. If you remember inside of our Houdini project, we actually set the vertex color of the inside to be blue, but that's not what's driving this color. This color is being set by this texture. You can change this and you can change what these inside pieces look like. So I'm going to set this to be pink. So now you can see that these inside pieces are set this way. And that's because we're using this vertex color, which we set up in Houdini, to drive what the color is here. So we're saying, okay, there's this value in the blue channel, and if this value is bigger than B or equal to B, set it to pink, which would be the value that we set. So that's all the inside pieces. And if you remember, the outside pieces are black, so they are obviously smaller, so they'll be this color. So they'll be white. So just to show you a little bit of how this works, I'm going to plug the blue channel into the color. You can see that these inside pieces are white because of us setting that vertex color inside of Houdini. And we're basically changing that color inside of Unreal based on the values. So now I'm just going to turn this pink color back to blue like I had it. And now let's talk about how I'm driving this animation with the vertex color. If you remember, each one of the planes has a different color value of red. So what I'm doing is I'm using that value to drive its animation. So this is just the red value, and then I'm multiplying it by 12. I'm just going to plug that into the display frame to give you an idea of what's going on. So if you go here, you'll see that each one of these planes, based on the color that we've set, has a different amount that it's broken apart. And that's because each plane has a different vertex color amount, and that's being multiplied by 12, and that sets how far through it's in its breaking animation phase. So as we go around, this piece over here is the furthest through its breaking animation, and this piece at the beginning hasn't broken at all based on its color values. So now we can go back here, and I'm just going to undo that. And we need this to loop through. We can't have it just be a static frame. We need this to be multiplied by a value that is changing. And that's why we have the time node here. We have it multiplied by speed, so we can change this in the material instance, and then we're doing a fraction, so we can get a fraction between 0 to 1. So if I just plug in this debug scalar values and say start preview, you can see that this is running through a 0 to 1 ratio. And this 0 to 1 ratio is going to be used to run through our animation. So each panel will be multiplied by this, and it'll basically have it run through its animation phase. Next, we need to compute the total number of looped frames, and we need to have an offset. So we want each panel to have an offset between its frames when they start breaking. So we don't want them to just start breaking one after another. We want there to be a little bit of delay between them. So I have my delay set to 40 right now. We're multiplying that by 12 because if you remember, there's 12 planes in total. And then 120 is the total number of frames that we set up in Houdini. So we're taking that offset, minusing it by the total amount of frames, and then we're adding it to the offset multiplied by 12. And then we're adding 120, and it's waiting for this many frames at the end. So at the very end of the entire animation, we're going to add 120 to the end. And then we're multiplying that by the frac. So basically, we're saying this number is going to be, I'll show you, 680. We're taking that and we're multiplying it by a fraction from 0 to 1, which is completing that animation. And then we're putting it here. And we're saying by the vertex color, subtract that amount by this. So we're saying we have this vertex color, which you can think of the red channel we have as each one of these planes has a different number. We're taking that number, multiplying it by 12, and then multiplying each one of these planes' number by 40 for the offset. So the offset per panel. So if you make this a smaller number, the planes will start to be rebuilt at a much faster rate because this determines how much we're waiting in between each breaking point, each breaking of the planes. And then what we're saying is, okay, 680 looping, if you look here, 680 looping is our number, and we want to take that and we want to subtract it by this number, the breaking of each plane's offset. And then we're going to take that, clamp it between 1 and 120. So now we're going from 1 to 120, 120 being completely falling down to the ground. So now we're having it to where each plane is just breaking apart one at a time, but we want the opposite. We want it to go from 120 to 1. So then we're saying subtract 121 from this number, which is changing. So now we're going from 120 to 1, which is completely rebuilt. So now that's done. So for example, just to show you, I'm going to plug this into the display override, and you can see each plane will now fall down one at a time because we've reversed the animation. So I'm just going to add that back. That's going to fix it. Each plane is being built up one at a time, and they're being offset by that number 40 for each plane. And if we change that, we can have them rebuild much faster. So I'm going to change this to 5. So by changing that number to 5, you can see here that there is a much smaller delay between each of the planes being built back up. They're all happening one right after each other. And if we set this to a smaller number like 1, they'd all be being rebuilt almost at the exact same time. So we keep it to 40 so that there's an offset in between each one being built. We want there to be a delay in between each plane being built up. So obviously we aren't applying this master material to the geometry, so we're going to apply the material instance. Before we do that, let's take our textures that we got out of Houdini, right-click, Scripted Asset Actions. Let's apply the side effects VAT HDR textures, and then open that material instance. And here's our parameter for the speed. So you can change this and it'll speed up this entire animation for all the planes. And then let's just drag and drop in our position texture and our rotation texture, and then it's all set. Then we just drag and drop this material instance onto the geometry, and we have this effect. Now let's talk about how to use VATs and render targets to create a destructible wall. The textures we got out of Houdini are the conditional VAT position, the VAT position F1, and the VAT rotation. If we look at the VAT position F1, each one of these pixels represents the pieces of our VAT destruction. And each of these pieces are only at the first frame of the animation, so they're at rest. You can think of the position F1 texture having the rest position for all of our VAT pieces, and it also has the radius of each piece in the alpha channel. Each pixel represents a piece of the VAT in its rest position. The VAT position texture holds the information for the entire animation. If you look at the texture itself, you notice that it's way longer than the VAT position F1, and that's because it's every single frame of that animation. The F1 texture is 128 by 16, and the VAT position is 128 by 1920. And that's because if you take 16 times 120, our frame range, you get 1920. So this is our entire animation, and this is just our first frame. For our conditional VAT, we also want to have different collisions than the ones that are coming in from our VAT static object. We want to have our collisions driven not by those pieces, but only by these planes. Inside Houdini, I've brought in our original static mesh, and I've merged it in with object merge. So I have two of these, and one of them is called UCX_glass01, and this UCX will allow Unreal to read it as collision geometry. So once that's done, I have these two objects here. I'm just going to go to export and export it as an FBX inside of our Unreal project. Once you've done that, open your mesh that is our original VAT mesh that we've exported. And what you're going to do is you're going to click on the mesh, the collision geometry mesh, which we got out, which we just exported. And then inside this tab, you're going to go to collision. You're going to say copy collision from selected static object. That way we're copying the collision of these planes onto our collision of our VAT static object. And that is because the VAT static object, all of these pieces are broken up. It's going to mess with our collision geometry. So we want the collision geometry to just be these planes. So we exported these planes with the UCX name tag. That way we can use it as collision geometry. When this mesh gets hit with a projectile, we want to be able to write out information like where it got hit and when it got hit. In order to do that, we need to set up some logic within our blueprints. With the material dynamic instance, you are able to change values of a material from the blueprint. So what we're doing is we're just setting up those material dynamic instances. We're basically telling the material, hey, I want to be able to change this from within my blueprint. So here we're setting it up for the imVat conditional instance, the render target previous frame, and the render target current frame. And we're also setting up certain parameter values like the render target this frame, the render target previous frame. The next thing we want to do is we want to set up when a projectile hits this mesh, we want to be able to take some of that information and put it into our material instance, which would be our render targets. So you can see here, we're getting the transform of our projectile actor and our mesh, and we're basically writing out values of transform information. So we're getting the XYZ of where this projectile is hitting our mesh, and we're baking that out into the RGB inside of our render target drawing, this frame. And then we're also getting the game time of when this hit. So basically, we're saying when there's a projectile that hits our mesh, we want to take location information, bake it into the RGB, and we also want to get the game time in seconds. We're going to take that information and we're going to write it to our render targets. Then we have a event actor end overlap, which says, don't update the render target if we've ended our overlap. Then we have an event tick with some logic here. And what this is doing is it continuously updates if the overlap event lasts for a while. So this is the material dynamic instance that the blueprint is writing to when there's a collision. So you can see here is the rest local position. And this is actually, once we set this up with a material instance, this is going to have that first position that we talked about. So it's going to have this position F1. So it has our rest data. So all the pieces not moving. And then we're going to take that data, and you remember the alpha is the radius. We're going to multiply it by 100 because from the conversion to Houdini to Unreal, you need to multiply by 100 to have the right size. So it's multiplying the radius of every single piece by 100 to be accurate. And then this overlap local position is actually what's being written out of the blueprint. So when there's a collision within our blueprint, that position data is written into here, and then we're comparing that distance to the first frame position data. So we're comparing those, subtracting, we're saying, hey, if the radius of these pieces is bigger than the hit position, then we have an accurate hit. And the last thing that we need to check for is we need to check that it hasn't already been written. So this has the render target previous frame. So we're just checking by the render target's previous frame to see, hey, has that piece already been hit? And if it hasn't, then it'll cause that animation to go off within our vat. So here we are in the master material that we're going to be using. So first things first, we need the UV coordinates to be the same size in order to sample them correctly. So we're going to take the G and we're going to multiply it by the frame number. If you remember the position F1, this size is not the correct size. So we need to multiply it so that they're the same in the UV coordinates. So like this one, it's 1920. We need to multiply this in the V by the frame range in order to be the same size as this. So this UV layout is used to sample the first slice of VAT and the entire render target. And they use a common source, which enables them to link up the piece with activation time because of this structure. So any point on this UV is all the vertices of one piece. So we're going to take this render target, and which is going to be the material instance, but right here it's just nothing. And this will have it correctly sampled. And then we can take that, and that's going to give us the information that we need. And we're going to say, if G is greater than 1, then we are going to subtract the current game time by the activation time. And that will give us how long that piece has been activated. And if it hasn't been activated, which would mean it's less than 1 or equal to, then it's just going to be like time minus time. So it'll still be set to 0. So nothing's happening. And the time loops, so you have to stop it before it gets too far to where the values aren't doing anything. So that's why we have it clamped here to 1.983, which is the duration of a single frame. So we're just making sure it's not getting out of hand. And yeah, that's how this is set up. So we're accurately sampling this render target for this vat to be able to sample that data. The last part of this material is just the metallic look. And I just copied and pasted the nodes from a metal material into this vat material. Once that's done, what you need to do is obviously make a material instance. Just right click material instance. And then in here, you just need to drag and drop your position and rotation textures that we got out of Houdini, and apply that to our mesh inside the blueprint. And once that's done, you successfully have a conditional vat. I hope you found this workshop useful, and enjoy Houdini 19.5.